I got started in high-performance computing back in when I was an undergrad. I was looking for a summer job, and I found out that Argonne National Lab was in my backyard and from where I was going to school, and took on an internship. And it was a great learning experience because everything I was learning in school I could apply directly to what I was doing at work and vice versa. So, I think I've always been a person that felt like if you can apply what you're doing in school to what you're doing in work and life, then it's just more meaningful. So I really liked that, and it was a great opportunity for me, and I liked it so much I didn't stop. So after I graduated from college, I tried to get on working in the material science division at Argonne National Lab, and because I didn't have a physics background but a computer science background, that wasn't going to work. So I got a job at the Central Computing Division at Argonne National Lab, where I worked for a few years. Worked on my master's degree at night at a nearby college. And so after that, I kept going. I got my PhD. I went from working for Central Computing to high energy physics on the Super Collider project, and then back to math and computer science, where I was working on my PhD work, which was the first IBM SP was at Argonne National Lab and at Cornell University. Cornell had the largest 512 node machine, and Argonne had a 128 node machine. And my new bosses at Argonne told me that my first day on the job that I could either figure out how to schedule this machine or hand schedule it by myself, around the clock. So when you have a problem, that's an opportunity, and so my opportunity was to develop a job scheduling system, which I did, and it was the first backfill algorithm-based scheduling algorithm. I went on and developed a heterogeneous backfill scheduling algorithm that was my PhD work, and that's actually how I got lured to Cornell. They had a real issue doing scheduling large parallel jobs on this is the largest IBM SP in the world, so it was a great opportunity for me to move on and work closely with IBM, and so here I am today. I've been at Cornell now for 15 years. I was at Argonne for a total of 10 years. I've been all the way from a systems programmer. Now I'm the director for the Center for Advanced Computing at Cornell University. It's a lot of fun. Different challenges from when you're a programmer. Some days I really miss the sort of getting my hands dirty and doing real work, as I call it. But now I get to sort of drive the vision and go after new challenges, and it's a lot of fun. Researchers are drowning in data, whether they even use computers or not. So they have instruments like gene sequencers and mass spectrometers and telescopes and all these different types of devices that produce data, and it's producing it at such a rate they can't make sense of it anymore. So many researchers are being forced to use computers that hadn't in the past, or did a little bit, but the problems are so much harder than before that they struggle. So that's where our center comes into play, and we help those users as best we can. What I've been most excited about and most interested in since my PhD work and moving into today, so over the past 15 years, is I think that it's important that high-performance computing, or supercomputing as we used to call it, becomes a utility and it becomes easy to use. That's the real challenge. We hear that everyone's focused on petaflops and exaflops, and that's really exciting, and it's an important yardstick to measure where the technology has come. But if you can't teach students about it and you can't let them try it, and it's really hard to get them excited about it. I think it's a big problem that we face today with getting kids excited about computer science and computational science, is that to get to touch those big machines seems like an impossibility. So I've been looking for ways to make it so that you can do high-performance computing right from the desktop, and we've worked with lots of companies on this, Microsoft in particular, and we were really happy that we just announced a new machine with MathWorks and Microsoft, and was funded by the National Science Foundation. And the really cool thing about it is that students today use MATLAB in everything they do. Right? They use it in class, they use it in their labs, and they don't have to be computer scientists to use the computer, and that's really cool. So what we've done is developed a new resource which allows them to scale seamlessly from MATLAB on their desktop to a large parallel machine, and they don't have to even know it. They install a config file and they're running in parallel, and it's sort of magic, and it works. And they start to realize the benefits of high-performance computing without having to know all the plumbing and all the coding behind the scenes. The other thing is that this model allows the researcher to focus on their research and not the computer science. And I think that's the most exciting thing. I think that's what's going to enable breakthroughs. If the software tools allow the researchers to stop focusing on all the plumbing and just focus on their science, I think that's where the next exciting breakthroughs are going to happen. And so that's been a goal of mine. Now I want to focus on not only the tools like MATLAB and things like that, but also on data analysis. So how do you move that data around? And once you have the data there, how do you find the really important pieces that you're looking for? So I think that's the most important challenge today, and those are the things that we're focusing on quite extensively at Cornell. So I think one of the technical challenges that we have today is really on this sheer scale issue. And so, you think about the multi-core issue, and researchers are struggling now with thousands of cores and how to effectively program that. And it's only going to get harder and harder. And I think companies or software vendors or even researchers that provide software tools that do that for you and let you solve the problems in a scalable way, I think that's going to be really a hard challenge. And I think it's not just scaling and running a benchmark and saying I can achieve this performance, but is that machine going to be reliable and really be a utility, or is it going to be something that flakes out and the researcher constantly is struggling with? I think that's an important challenge. The other challenge that I think many academic and even business computing centers are faced with is sustainability models. What's your value proposition, especially with the advent of the cloud? People are wondering how the cloud's going to play in high-performance computing, and when do you use the cloud, and when do you not use the cloud, and when do you do your own thing, and when do you outsource it? And this is a real challenge, and I think the most important thing that I firmly believe in is that the people are the difference. If you don't have people that can help the researchers apply these tools to their research, they're not going to get used effectively. And so, again, this points back to this whole education issue. We have to get kids in high school excited about science, excited about computing, get them to think about going into science fields in college and learning these skills early. And I think sometimes we force them into a computer science field to learn how to program, but more and more, all these fields require it. So tools that can let them use computers effectively and focus on their research are going to be essential. My inspiration is not in standing up gigantic computers and having more data than anybody else. My inspiration is helping people, and I have a staff of people that feel that way too. And I think that's just a great feeling to know that you go to work every day and you have impact, that you're helping someone solve really, really important problems that could have a real impact on society. I think that's really, really exciting. And all the things that you do underneath are technology, and they're tools, and they're things that you can buy or plug together, sort of like building your own solution with Lego blocks. And that's great, but the ultimate success of researchers and having an impact on society is just the best. If you're afraid of change, you don't belong in anything computational or computer oriented, but that's exciting, right? Coming to work every day and knowing that you could have a breakthrough, or you could do something that's never done before, or you could help someone, solve a problem that's never been solved. That's really exciting, and I think that's what sort of, turns me on, and I think turns a lot of people on that finally get into this. My personal thing is working with the Weill Cornell Medical School. We've had an opportunity to help some groups, and the thing that excites me about that is that there you have an opportunity to really help people and make a difference in people's lives. If you can help come up with a solution that means the doctors and the people doing medical research can help people, that are sick or fighting disease get better, that's a really great feeling. And so that's I think my most exciting focus right now is trying to help those people and understand what they need and provide it in a way that makes them very efficient and very effective.